Hello, curious minds. What if everything we thought we knew about the universe's expansion was wrong? What if dark energy, the mysterious force we've been chasing for decades, doesn't even exist? Today, we're diving into the Timescape Hypothesis, a bold new idea that could change the way we see the cosmos forever. Let's start with a big mystery. Back in 1998, two teams of scientists were studying distant exploding stars called Type Ia supernovae, using powerful tools like the Hubble Space Telescope and the Keck Observatory. These supernovae are like cosmic lighthouses. They shine with predictable brightness, making them perfect for measuring vast distances in the universe. But what they found was shocking. The light from these supernovae wasn't just redshifted, which means the galaxies hosting them were moving away from us. It was redshifted more than expected. In other words, these galaxies weren't just receding. They were speeding up over time, as if some mysterious force is pushing them further. This was the first evidence that the universe's expansion was accelerating. To explain this cosmic acceleration, scientists proposed a mysterious new ingredient in the universe: dark energy, a kind of anti-gravity force that pushes everything apart. According to the current model, dark energy isn't just a small player, it dominates the universe, making up a whopping 70% of its total energy. But here's the catch: we've never actually seen dark energy. We don't know what it's made of, how it works, or why it exists. It's one of the biggest mysteries in science today, and that's where things get interesting. What if the acceleration isn't caused by dark energy at all? What if it's not a force pushing galaxies apart but rather an illusion, a side effect of the universe's uneven structure? You see, the cosmos isn't perfectly smooth. It's full of dense clusters of galaxies, thin filaments, and vast empty voids. What if this patchwork of structures is messing with the way we perceive cosmic expansion? That's exactly what the Timescape Hypothesis suggests. Now that we understand the mystery, let's talk about the Timescape Hypothesis, an alternative idea that doesn't need dark energy to explain why the universe appears to expand faster. Proposed in 2007 by Professor David L. Wiltshire from the University of Canterbury in New Zealand, it suggests that differences in how time flows in dense regions versus cosmic voids could create the illusion of acceleration. Recently, researchers have revisited this idea, using modern data and technologies to test its predictions and address cosmological anomalies. This renewed attention highlights the hypothesis's potential to reshape our understanding of the universe. Here's the key idea: the universe is not uniform. It's not a smooth soup of galaxies evenly spread out. Instead, it's a cosmic patchwork of dense clusters of galaxies, thin filaments, and enormous empty voids. And this uneven structure is critical to understanding the Timescape Hypothesis. Why? Because gravity, which comes from matter, doesn't just pull things together, it also affects time. In regions where there's a lot of matter, like dense galaxy clusters, gravity is stronger, and strong gravity slows down time. Meanwhile, in the vast cosmic voids where there's almost no matter, gravity is weaker, and time flows faster. Here's a simple way to imagine it. Think of the universe as a road trip. The dense, urban area will represent a galaxy cluster, where there are lots of stoplights and slow-moving traffic. Time crawls. But out on an empty highway, which is like the cosmic voids, there's no traffic, and time flies. Now we know that this isn't a perfect example, but it gives you the idea. The flow of time depends on the density of matter around it, and this difference is a key piece of the puzzle. So, how does this explain the universe's apparent acceleration? Let's say we're observing distant galaxies from Earth. Our galaxy is in a relatively dense region of the universe where time flows slower than in those vast empty voids. When we look at light traveling to us from galaxies near these voids, we're essentially seeing time pass more quickly for them compared to us. It's like watching a sped-up video. It can look like those galaxies are moving away faster, even if they're not. Now here's where it gets interesting. When scientists calculate the average expansion rate of the universe, they treat it as if time and space are the same everywhere. But they're not. The Timescape Hypothesis argues that these differences in time, caused by the uneven structure of the universe, create an illusion of acceleration. In reality, the universe might be expanding steadily without the need for dark energy at all. Think about it. What we perceive as a mysterious force pushing galaxies apart could just be the result of living in a universe where time flows differently in different regions. Instead of inventing dark energy to explain the acceleration, the Timescape Hypothesis suggests that we just need to adjust how we're looking at the data. It's a bold idea that challenges the current model of cosmology, and while it doesn't completely overthrow our understanding of the universe, it offers a new perspective. Okay, so the Timescape Hypothesis sounds fascinating, but how do scientists test if it's true? After all, science is all about putting ideas to the test to see if they match reality. One of the primary tools scientists use are Type Ia supernovae, the exploding stars we mentioned earlier. These are incredibly useful because they act like cosmic standard candles. We know their intrinsic brightness, which means we can compare how bright they appear from Earth and calculate how far away they are. If the timescape hypothesis holds true, the light from these supernovae traveling through different regions of the universe, with varying time dilation effects, should appear different. To test this, astronomers measure the redshift of the supernovae, which indicates how much the light has stretched as it travels through space. The key test here: if time is flowing differently in dense regions of the universe compared to voids, the supernovae in different parts of the sky should show subtle differences in their redshift. By comparing data from multiple supernovae in different cosmic environments, scientists can figure out if the timescape model explains these differences better than dark energy. Next, we have the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. This radiation is like a snapshot of the universe when it was just a few 100,000 years old. By studying the CMB with precision instruments like the Planck satellite, scientists can measure tiny variations in temperature and density across the universe. If time dilation is at play, it could subtly affect the patterns we observe in the CMB. The timescape hypothesis would predict certain differences in how the CMB looks across regions of space, depending on the time dilation effects of gravity. This means scientists would look for discrepancies in the CMB data that don't quite fit with the standard dark energy model. The beauty of the CMB is that it's a snapshot of the early universe, so it offers a unique opportunity to test the hypothesis against some of the most fundamental cosmic data. And here's where it gets really exciting. The timescape hypothesis doesn't just rely on existing data, it makes new predictions. For instance, it suggests that galaxy motions in large-scale structures should follow certain patterns based on the flow of time in voids versus clusters. Large-scale surveys such as the Sloan Digital Sky Survey, SDSS, or Dark Energy Survey, DES, measure the positions and velocities of millions of galaxies across the universe. If the timescape hypothesis is correct, galaxies in dense clusters should show different motion patterns compared to those in vast cosmic voids. By analyzing how galaxies move and how clusters and voids behave, scientists can check whether the expected patterns of motion match up with predictions from the timescape model. If time dilation is causing the illusion of accelerated expansion, we might see slight differences in galaxy velocities that don't match the predictions made by the dark energy model. But like any revolutionary idea, the timescape hypothesis has its skeptics. Critics argue that dark energy explains the data more simply, and that the hypothesis needs more precise predictions to compete. This is why testing it thoroughly is so important. The great thing about science is that it's self-correcting. Whether it ultimately replaces dark energy or not, testing this hypothesis moves us closer to the truth. So the timescape hypothesis is a challenge to our current model of the universe, and scientists are actively working to see if it holds up to the evidence. The big question is, will it pass the test? So, why should we care about the timescape hypothesis? What makes it more than just an interesting idea? Well, it challenges one of the cornerstones of modern cosmology: dark energy. If the timescape hypothesis is correct, it could mean that 70% of the universe, the dark energy, doesn't exist at all. That would completely change the way we understand the cosmos and force us to rethink decades of research. But the importance goes even deeper. The timescape hypothesis offers us a new perspective on the universe, one that accounts for its true complexity. Instead of treating the universe like it's smooth and uniform, it embraces the fact that the cosmos is a patchwork of dense clusters and vast voids. By considering how time and space behave differently in these regions, we might be able to solve one of the biggest mysteries in physics without introducing something as mysterious as dark energy. And here's another point: if the timescape hypothesis is correct, it could help us refine the tools we use to measure the universe. Things like supernovae, redshifts, and cosmic microwave background radiation. All of these might need to be reinterpreted with this new understanding of time and space. In other words, it could give us a more accurate picture of how the universe works. Finally, there's the philosophical impact. The timescape hypothesis reminds us that our understanding of the universe is always evolving. It shows us that even when we think we've solved the big questions, there might still be deeper layers of truth waiting to be discovered. And there you have it, the timescape hypothesis. Could this really mean the end of dark energy as we know it? Or is it just another piece of the puzzle in understanding our universe? Let us know what you think in the comments below. If you enjoyed this video, don't forget to hit that like button, subscribe for more cosmic explorations, and ring the bell so you never miss out on our next journey through the universe. Thanks for watching. Until next time, keep looking up.